While operating wind farms is critical to the energy transition, it also comes with certain vulnerabilities. We face constant risks that can compromise the efficiency and safety of our facilities. These challenges range from unexpected mechanical failures to extreme weather conditions and communications disruptions. The need for robust and adaptable crisis management is therefore imperative. It's not enough to react, it's essential to anticipate and mitigate the impact of these events. Operational continuity and asset protection are non-negotiable priorities in this strategic sector. Today, we'll discuss a multi-agent system, a solution designed to revolutionize crisis response in wind energy. This system is aimed at operations managers, plant managers, reliability engineers, and maintenance managers. Its primary objective is to protect assets and ensure the uninterrupted operation of wind farms. This innovative approach redefines incident management, transforming the way we address operational complexities. It provides a layer of intelligence and autonomy that traditional systems cannot offer. Its commitment is to resilience and efficiency in an increasingly demanding environment. The multi-agent system is based on decentralized intelligence and a proactive approach. Each component of the wind farm, from the individual wind turbine to the communication subsystems, has autonomous processing and decision-making capabilities. This enables an agile and localized response to any eventuality. Management is oriented toward anticipation and prevention, rather than mere reaction to already manifested problems. This paradigm shift is crucial to minimizing damage and downtime. Proactivity is integrated into every layer of the system, from detection to resolution. The key features of this system are its fundamental pillar. First, local autonomy with global supervision. Each turbine operates with its own intelligence, capable of making critical decisions, while a central orchestrating agent coordinates and optimizes actions at the farm level. This duality ensures both agility and strategic coherence. Second, intelligent alarm prioritization. The system not only detects anomalies, but also filters and prioritizes them based on their criticality and potential impact. This ensures that maintenance and operations teams focus their attention on the most urgent issues, avoiding information overload. The relevance of information is key to an effective response. Third, structured and explainable escalation. All decisions and actions taken by the system are documented and justified. If an incident exceeds certain predefined thresholds, the system transparently escalates the situation, providing a complete record of the logic involved. This facilitates auditing and continuous learning. Finally, cascading failure prevention is a vital capability. The system is designed to prevent a localized failure in one turbine from propagating and affecting the entire wind farm. Through intelligent isolation and dynamic reconfiguration, the operational integrity of the entire wind farm is protected. The farm's resilience is maximized in the face of adverse events. To illustrate the robustness of the multi-agent system, we will analyze 3 simulated crisis scenarios. These examples demonstrate how the system addresses complex challenges, overcoming the limitations of traditional approaches. The system's responsiveness is its greatest strength. Consider a sudden failure in a wind turbine's gearbox. The system instantly detects irregular vibrations and a sudden rise in temperature in the bearing. There is no time for long-term predictions. The situation is imminent and requires immediate action. The system initiates a safe shutdown sequence for the wind turbine, protecting critical components from further damage. Simultaneously, it prioritizes maintenance resources, generating an immediate work order for repair. The entire process, from detection to action, is documented with all relevant signals. The result is a controlled shutdown that prevents further damage, such as converter failure. The repair is planned within an optimal time frame, minimizing downtime. A potential cost of tens of thousands of euros in damage is prevented, demonstrating the system's preventive effectiveness. Imagine a severe thunderstorm with wind gusts exceeding operational limits and lightning detected just a few kilometers away. This poses an extreme risk to the wind farm's infrastructure. Asset safety is the top priority in these conditions. The environment agent communicates the extreme risk condition to the orchestrator agent. The system proactively triggers a phased shutdown protocol for the wind turbines, protecting them from potential lightning strikes and hurricane-force winds. Critical data is securely stored in edge computing. Additionally, any unauthorized remote access is blocked by the cybersecurity subagent, ensuring data integrity and control. The system's preemptive action prevents catastrophic damage. The farm is placed in safe mode, ready for controlled restart when conditions improve. Wind data and other environmental parameters are stored for later analysis, improving future system responses. Here, the value lies not in production, but in investment protection. Now, consider a massive SCADA communications failure scenario, such as a fiber optic outage that leaves 30 turbines without connectivity to the control room for 40 minutes. The inability to monitor and control from the central SCADA represents a critical challenge. In this situation, the data architecture subagent activates intelligence at the edge of each turbine. Each local control agent operates in autonomous mode, following predefined safety rules. Production continues under safe parameters without external intervention. Critical alarms are stored locally and automatically forwarded upon restoration of connectivity. The explainability agent generates a complete report of everything that occurred during the outage, with no data loss. 100% traceability is achieved, even in the absence of central communication. The result is continuous production under safe parameters, zero operational incidents during the outage, and complete traceability of every event. The system demonstrates its ability to maintain operability and security, even when the communication infrastructure fails. Resilience is a fundamental pillar of our multi-agent system. What happens if the failure originates from the artificial intelligence system itself, for example, an error in updating a predictive model? This is a scenario that has been considered, and for which we have developed debugging mechanisms. The system incorporates continuous learning and self-validation mechanisms. If statistical deviations or anomalous performance are detected in a predictive model, the continuous learning agent identifies them. The automatic retraining subagent reverts to a previous, validated version of the model. The explanation-generating subagent notifies the failure and justifies the reversion, maintaining transparency. A technical committee receives the alert and the revision proposal, ensuring human oversight. This guarantees operational integrity and confidence in the system. Automatic recovery, complete transparency, and a documented history of decisions are the expected results. Confidence in the system is strengthened, not lost, because a good system not only prevents errors, but also recovers from them. Human-machine collaboration is crucial in crisis management. The multi-agent system does not seek to replace the human supervisor, but rather to assist, inform, and anticipate their needs. It provides real-time information and in-depth analysis for informed decision-making. Supervisors retain ultimate control, with the ability to validate, pause, or override any action proposed by the system. Every decision and action of the system is traceable and technically justified, offering complete transparency. This allows for effective oversight and human intervention when necessary. The system acts as an intelligent co-pilot, amplifying human capabilities and enabling more serene and effective crisis management. It's not about turning off alarms, but about making calm decisions amidst chaos. The capabilities of the multi-agent system significantly surpass those of traditional systems in several key aspects. In detection, we move from a manual and reactive approach to a predictive and autonomous one, identifying problems before they escalate. Anticipation is key. In response, the system offers distributed and intelligent management, in contrast to the rigid centralization of conventional systems. Each agent acts autonomously, yet in a coordinated manner, optimizing the response. Agility is essential in critical situations. Incident escalation is flexible and context-based, unlike rigid, pre-established protocols. The system adapts to the specific situation, ensuring a proportionate and effective response. Informed intelligence is a key differentiator. The event log is complete, traceable, and explainable, unlike the partial or incomplete records of traditional systems. Every action and decision is documented, facilitating auditing and learning. Transparency is complete. Finally, oversight is greatly enhanced by the collaboration between intelligent agents and humans. It is not just oversight by people, but oversight enhanced by artificial intelligence. This increases the quality and efficiency of management. This system represents a fundamental shift toward proactive management. It's not about adding more sensors, but about empowering every existing sensor with intelligence. It mitigates the impact of unforeseen events, transforming vulnerability into resilience. The intelligence behind each piece of data is what makes the difference. Crises are inevitable in any industrial operation, but the impact is not defined by the failure itself, but by the ability to respond. A smart wind farm is not one that never fails, but one that continues to operate even when everything else seems to collapse. Resilience is the new metric of success. This multi-agent system is the next evolution in wind asset management, ensuring operational continuity and investment protection. In our next video, we will explore the system's adaptability to various wind farm configurations, including hybrid offshore installations with batteries,